When you pop that hood, you expect to see something that works, something that makes sense. But not every engine out there was built to make sense. Some were designed with the confidence of a genius and performed with the reliability of a broken blender. These are the engines that promised the world but delivered a headache, an empty wallet, and sometimes a ride on a tow truck. Some were underpowered, some self-destructed faster, and a few, well, they should have stayed on the drawing board. But let's skip the stories and see the 7 worst engines of the worst ever made or invented. The first one, it's the Isuzu 4JJ1TC engine is far from a disaster, but like any power unit, it is not immune to its fair share of headaches. Known for its strong build and decent reliability, this diesel workhorse is commonly found in Isuzu pickups and SUVs. However, owners quickly learn that the secret to keeping it happy is proper maintenance, because a few common issues can creep up and turn a dependable engine into a stubborn one. One of the most frequently reported problems is with the suction control valve. When this valve gets blocked or sticks, the engine can struggle to start, feel sluggish, or completely lose power under load. Fuel injector issues are another known weak point. Over time, the injectors can fail, leading to rough idling, black smoke from the exhaust, poor fuel efficiency, and a noticeable dip in overall performance. Then there is the EGR valve, which tends to get clogged with soot from exhaust and crankcase fumes, cutting down its effectiveness and affecting smooth running. Overheating is another concern, often caused by simple but damaging culprits like a clogged radiator, a bad thermostat, or poor quality coolant. The cam angle sensor can also cause trouble when moisture gets into the plug, leading to corrosion and unreliable starts. Oil pressure loss has been reported in some models too, usually due to a clogged oil pickup tube, a weak oil pump, or a faulty pressure sensor. And while it is not a catastrophic failure engine, the 4JJ1TC does have a reputation for injector wear and higher than expected oil consumption over time. These issues may not blow the engine up overnight, but they can lead to more frequent visits to the garage and rising maintenance bills. And if you have been with us this far, it honestly means a lot. A simple subscribe from you helps us grow and keep bringing stories like this straight to your screen. It may look small, but let's get back to it. The Ducati Eleanor 868 engine is not your typical V8. It is a one-off experimental build created by German engineer Dieter Hartmann-Orthwein, not by Ducati itself. The engine was designed to push the limits of what could be done with unconventional engineering. Built from Ducati 900 components, it displaces 868 cubic centimeters and produces around 80 horsepower. What makes this engine truly unusual is its connecting rod design. Instead of 8 rods, it uses a single Y-shaped connecting rod per cylinder bank to drive 4 pistons in a row. The outer pistons are linked to the inner ones using small pivoting rods. This reduces weight but also creates significant stress on the metal under compression and tension, limiting how far the engine can be pushed. It is a 90-degree SOHC V8 built in 2007 and was mounted into a Ducati 900 SS. At 7,500 revolutions per minute, it produced roughly 70 horsepower, slightly less than the stock engine, but it had less reciprocating mass, making it lighter and more responsive. This engine was never meant for mass production or extreme performance. Its purpose was to showcase creativity and mechanical ingenuity. The concept is fascinating, but its complex rod system and limited durability make it impractical for real-world use. But now this engine founder should have been confused. The BRM H16 engine was one of the most ambitious and problematic engines ever built. Developed by British Racing Motors in the 1960s, it featured a 3-liter, 16-cylinder H configuration created by stacking 2 flat-8 engines on top of each other. The idea was simple: more power through innovation. The result was anything but simple. For performance, BRM expected around 500 to 600 horsepower, but the real-world output sat closer to 400 horsepower. The stack design gave it a high center of gravity, which made handling unstable. It was also much heavier than rival engines, and its extreme complexity made it prone to mechanical failure. In fact, it retired from 30 out of 40 races in a single season. Mechanically, it had 8 camshafts, 64 valves, and 2 interconnected crankshafts. The cooling and lubrication systems were complicated, requiring dual pumps and twice the oil of a V12. This added even more weight and more points of failure. While its unique sound and compact length were impressive, its constant breakdowns, excessive fuel use, and reliability issues made it one of the most frustrating engines to run in Formula One history. You would expect something called an ecotic engine to be efficient and dependable, but the Z22 engine from Opel proved to be quite the opposite. This 2.2-liter 4-cylinder unit found in models like the Opel Vectra, Chevrolet Malibu, Saturn Vue, and several others was notorious for turning simple ownership into a long-term headache. It came with a complex timing system where the tensioner often wore out too quickly or even tore off completely, and when that happened, the entire engine was at risk. To make matters worse, this engine was paired with a problematic injection system which only amplified the failures. The so-called eco-friendly motor also burned through fuel and oil far more than it should have, leaving owners topping up constantly. The issues didn't stop there. The Z22 was infamous for excessive oil consumption and oil sludging, especially when maintenance schedules were not followed religiously. Poor heat management was another ticking time bomb. With weak thermal insulation around the turbocharger, the engine overheated easily, which often led to crankshaft bearing failure and catastrophic internal damage. It was extremely sensitive to neglect, and skipping or delaying oil changes almost guaranteed a blown engine. Over time, this gave the Z22 a reputation as one of the least reliable eco-deck engines ever made. It may have looked affordable on the surface, but owning one felt more like walking on a landmine. The early General Motors LT4 supercharged engine promised greatness but delivered headaches, especially in its first years. This 6.2-liter powerhouse pushed out 650 horsepower and gave cars like the Corvette Z06 and Camaro ZL1 serious muscle, but its flaws showed up fast. The biggest culprit was the oil pump. Early units had weak housings and bypass valve failures that starved the engine of oil, often leading to catastrophic failure with little warning. Weak valve springs made things worse, snapping under stress, while the active fuel management system sometimes caused valves to stick, damaging the camshaft and lifters. Then came the heat. The supercharger struggled to shed it, forcing Corvette Z06 engines into limp mode after just a few spirited laps, a major blow to a car built for the track. General Motors eventually redesigned the oil pump and improved quality, while owners turned to stronger aftermarket parts and AFM deletes to fix the problem. But the early LT4 remains a reminder that raw power means nothing if your engine is busy trying to blow itself up. You all know Subaru's 2.5-liter turbocharged engine earned a loyal fanbase for its performance and punchy acceleration. But beneath that power lay some notorious weak spots that ruined the ownership experience for many drivers. The biggest culprit was oil consumption and starvation, a problem that often showed up without much warning. Due to a flawed oil supply system, the engine sometimes failed to receive enough oil, especially during aggressive driving. When that happened, bearings and other components would start to wear out before overheating even became visible. The positive crankcase ventilation system was another weak link, allowing oil to accumulate in the intake, which led to increased oil consumption. On top of that, clogged oil pickup tubes and sludge buildup from neglected oil changes made matters worse, essentially choking the engine of its lifeblood. Head gasket failure was another major headache. Older versions of the EJ25 engine came with inferior gasket designs that were prone to failure around the 100,000 to 150,000 mile mark. As coolant degraded over time and turned acidic, it corroded the gaskets, leading to leaks between the cylinder head and engine block. Infrequent coolant flushes only sped up this failure, leaving many owners with expensive repair bills. To make things even more frustrating, oil leaks from various seals and gaskets were common even without total engine failure, slowly bleeding oil and leaving messy spots under the car. Timing belt tensioners and idler pulleys also had a reputation for letting go on older EJ engines, sometimes leading to catastrophic damage when the belt slipped. Over the years, these issues became so widespread that Subaru faced a class-action lawsuit for overheating, engine seizures, and sudden power loss in models like the WRX and WRX STI. What was supposed to be a rally-bred hero ended up being a cautionary tale about how power means nothing if the engine cannot keep itself alive. The Porsche MA 175 is a textbook case of how one critical engineering flaw can overshadow everything else a power plant does well. This flat-six engine, used most famously in the 2014 GT3, had the kind of high-revving character and raw excitement that made Porsche purists grin like kids in a candy shop. But under all that engineering brilliance, it hit a ticking time bomb: the connecting rod bolts. These bolts were the Achilles heel of the MA 175. They had a tendency to snap, and when they did, the entire engine would fail catastrophically, usually with no second chances. This was not a slow, gradual problem. It was sudden. One moment the engine was screaming toward its red line, the next it was a very expensive paperweight. But the nightmare did not end there. With the removal of the intermediate shaft in this generation, the timing chains were forced to spin at higher surface speeds, which made them more prone to failure. The oil pump drive chain also had its weak moments, occasionally breaking and cutting off oil flow entirely. In some cases, bore scoring became another headache, especially in colder climates where tight tolerances and cold starts did not mix well. If owners skipped proper warm-up, the cylinder walls could take a beating. Porsche, to its credit, did not bury the problem. When the connecting rod bolt issue surfaced, the company replaced the engines under warranty, at a cost that could range from $40,000 to $76,000 if a core was not returned. They also introduced improved piston coatings and adjusted clearances in later models to prevent further bore scoring issues. The MA175 is remembered not because it lacked performance, but because it showed how even the best driving cars can be undone by one crucial weak link. And for the 2014 GT3 owners, that weak link came in the form of a tiny bolt with a very big attitude problem. Thanks for sticking with us to the end. If you enjoyed this breakdown, make sure to hit that like button, drop a comment on what engine you want exposed next, and of course, subscribe so you don't miss the next mechanical heartbreak.